Okay, let's start our new unit. This is our fourth unit of the year. It's actually a combination of one section that we skipped over in Chapter 4 and all of Chapter 6, and it's on probability. And this is very exciting for me. Probability is my specific area of math that I love the most, so you'll get to see some wild-eyed grins from me this chapter. It's going to be a good one. The reason that we skipped over 4.3 earlier, and we're doing it now, is a lot of the time the data is presented in a table like this. It's called a two-way table. 4.3 is actually called relations in categorical data, but basically it's about data expressed in this way. A two-way table is a table like this, as you can see, and it compares two categorical variables. And this is me looking into the future and seeing our AP exam scores from the spring. And one thing that might be jumping out at you is why, if it's a categorical variable, why is there a 5, a 4, and a 3 up there? Sometimes we sort of number our categorical variables. The AP people could just as easily score us excellent, good, average, bad, terrible, and it would be just the same. So sometimes, even though there are numbers present, it's more like a categorical variable, and so that's okay for this particular two-way table. So these are our AP test scores, and you can see there are no 1s and 2s because that's not going to happen for anybody. We're all 3s, 4s, and 5s. And so take a minute if you haven't already, maybe pause and write this table down. And I want to just give you some features of it. First of all, we have two variables combined. We have a row variable and a column variable. Our row variable in this case is gender, because that's what's shown on the rows. Column variable is the AP exam scores. And then you've got a column and a row for the totals, and the totals should add up both ways, which just makes sense. But that's our first set of terms, row variable and column variable. Now, within this table, we will have a couple kinds of distributions. The first kind of distribution is called a marginal distribution. So just list these terms and refer to them in your table. And as it sounds, marginal distribution is found in the margins of the table. So there are two marginal distributions. One of them, each marginal distribution completely ignores one of the variables. That's the way I like to think of it. And if you just look at the margin, here's one marginal distribution. Right, if you just look at the exam scores, we have a breakdown of the 3s, 4s, and 5s, and there is nothing there. The gender is completely ignored. This bottom row of our table, it's found in the bottom margin, has nothing to do with gender. So you can graph your marginal distributions. So for us, in this case, one of the two marginal distributions, and I've got my 5 first, but down here I'm going to put 3, 4, 5. I've got, this is the AP grade, and this is the number of students. And let's see, I've got 27, 24, and 23, so I'm just going to make this 10, 20, 30. And I'm going to make a bar graph. That's the best way to graph a marginal distribution. I have 23 3s, and I have 27 4s, and 24 5s. So there's an example of a marginal distribution. If you look at this graph and you look at those numbers, gender is nowhere included in that breakdown. This just tells you, how did my 74 students do on the AP exam? So the other example of a marginal distribution would be up here. You could look at this table and only pay attention to the right-hand margin, again called marginal because that's where it is. It's on the edges of the table, on the margins. And I could just break down male and female, 38 and 36. And if you didn't really care, if this same table would, if you're just curious about how do KP stats classes break down male versus female, then you can tell from this table they're pretty close. This is obviously just a very simple example that I've made up, but you get the idea. Marginal distributions are found in the margins, and they only pay attention to one variable at a time. All right, so the next type of distribution, this chart. Alright, sorry about that. The next type of distribution is called a conditional distribution. A conditional distribution looks at one specific value of one of the variables. However many rows and columns there are in your table, that's how many conditional distributions there are. For our specific table, there are 6, and here they all are. Here's one. This is a conditional distribution. Here's another. Here's another. That's just looking at the 5s, 4s, or 3s, completely separate. And another would be the males, and another would be the females. So we have 5. I think I said 6 in a minute. We have 5 conditional distribution. Just look at one row or one column. Okay, so what's the purpose of conditional distribution? We have, let's look at the one of everybody who got a 4. In other words, under the condition that you got a 4, tell me about the distribution. Okay, so we have just the 4s. We had 8 and 19. Males, females. This would be, students who got a 4 in my title. I had, let's say that's 10 and 20. I had 8 guys, 19 ladies. Number, gender. So it doesn't completely ignore one of the variables. It just focuses on one specific case of the variable. So students who got a 4, I had 8 guys, 19 guys. I could also just look at the males or just the females. If I was just curious on how guys are doing after taking my class, and I wanted to only ignore the ladies' numbers for a minute, I would 16, 14. Was 16. I spent too much time on the graph. But this is males scores. This is how many. This is the score. That's another condition. Under the condition that we're only looking at the guys, tell me how the scores broke down. So that's 2 examples of distributions that are found within the two-way table. Marginal, conditional. Make sure you have an example down of those and you're able to use those terms. All right, one more little aspect of this section. Not a lot of calculating yet of probabilities and stuff like that. We're just getting the terminology down, getting familiar with this table. This is a pretty cool little part. Simpsons Paradox. Here's an example of a two-way table, and I've kind of got 2 categories with 2 subcategories across the top. Let's say there's a big university, UK, whatever. There's a business school and a law school. There are males and females, and the number who applied and were admitted and the number who applied and were denied. So let me ask you a couple questions about this setup, and we'll see where the paradox comes in. Paradox is just something that doesn't make sense. So question number 1 is, what percent of males, females were admitted? Okay, so overall, putting both schools together, we had let's see, 480 and 120 males applied to the business school, so that makes 600. And then with these other 100, we had 700 males apply to this college, to this university. We had 200, 3, 4, 500 females applied to the university. Okay, so overall admitted, we had 490 out of 700 males. And overall admitted, we have, out of 500 females, we had 280 out of 500. All right, so 490 out of 700 and 280 out of 500. So 490 out of 700 was 70%. I should have known that. 70% of our males were admitted. And 280 out of 500, I should know that one too, that looks like 56% of females were admitted. Okay, so overall, the entire school admits 70% of the males that apply, 56% of the females. So let's look at the different colleges sector. So business school. In business school, the males, we admitted 480 out of 600, which is, I should probably know that too, but I'm not sure, 480 out of 600. We admitted 80% of the males to business school. And females, we admitted 180 out of 200, which is 90%. So the business school alone admitted 90% of the ladies, 80% of the guys. Law school admitted, let's see, the males, they admitted 10 out of 100. And I do know that one. 10% of guys. And then we admitted 100 out of 300 ladies. Okay, so 100 out of 300, that's a third, 33%. This is Simpsons Paradox. All right, take a look at those numbers and see if something doesn't make sense. It doesn't add up. My first question was, overall, both colleges put together, who gets admitted most? Well, males were admitted 70% of the time. If you take those same people, we didn't change what table this data was coming from. We took the same people and looked at them at two separate colleges. Who does the business college admit at a higher rate? Well, they admit 90% of ladies. The law school, 33% of ladies, both of which are higher than the percentage for the males. This is called Simpsons Paradox. And this will happen when you've got kind of an uneven distribution of your variables. If you have a lot more applying to business school for the males than the law school, and stuff like this can happen. This is kind of a neat little puzzle of why it works out that way. I don't know that there's a great answer of why it happens. It just happens in certain distributions. So know that name, know Simpsons Paradox, and know what it means. Right? When you look at all the data together, one percentage is higher. But when you break it into its two parts, it looks like it's completely opposite. So that'll do it for 4.3, the start of our fourth unit on probability. And I will see you here, and I am so excited. We're going to talk probability.